Making sense of QFT. Lecture 6. Feynman's renormalization. In our previous lecture about QED, we arrived at some conflicting results. On one hand, we established that some physical predictions of our theory, such as cross-sections for electron-electron and electron-photon scattering, agree with experiment pretty well. This is an encouraging sign that we are on a right track, and that higher orders of perturbation theory may give us even better agreement with measurements. However, we also found an unacceptable divergent S-matrix contribution that we interpreted as electron self-scattering. Perhaps we can simply ignore these unphysical renorm terms and focus on real physical events? No. Unfortunately, this is not possible. It appears that in higher perturbation orders, we obtain infinite contributions to physical processes as well. Feynman diagrams of these terms contain closed loops, which correspond to divergent momentum integrals. Here are two examples of fourth-order electron-electron scattering diagrams with loops. Their resulting S-matrix contributions are infinite. And this is an example of a divergent diagram for electron-photon scattering. To fix the above problems, we have to apply so-called renormalization. The basic idea of this method is rather simple. First, we have to admit that the QED Hamiltonian that we were using so far is incorrect. Our problems will be fixed by modifying this Hamiltonian. More specifically, this modification will be done by adding special correction terms that we will call counter terms. In order to select counter terms, we will formulate physically meaningful renormalization conditions. There are three renormalization conditions. First, we demand that our S-matrix has no renormed terms in its expansion. We saw in our last lecture that the presence of renormed terms leads to a divergent S operator. This is unacceptable. Second condition relates to scattering cross-sections in the low energy limit. These quantities are well known from classical physics and experiments, and it is reasonable to demand that our calculated cross-sections converge to these established results in the low energy limit. Finally, we want to keep the relativistic invariance of our theory. So we will demand that the counterterms are obtained by Weinberg's rules as space integrals of Lorentz scalar field products. Without further ado, I will simply show you how these counterterms look like. For comparison, I remind you the potential energy density that was used to construct the original QED interaction. R of x tilde is the counterterm density required to satisfy the mass renormalization condition. Here we have our familiar Dirac quantum fields. Delta and epsilon are so-called renormalization constants whose values will be adjusted to satisfy renormalization conditions. W of x tilde is the charge renormalization counterterm density. Sigma is yet undefined renormalization constant. After scalar renormalization densities are established, our new Hamiltonian can be obtained from the original one by the addition of two operators, R and W. The new Hamiltonian will be marked by the subscript C to remind us that it contains counterterms. I haven't shown it here, but true QED has one more counterterm, which is supposed to compensate the presence of electron-positron loops. But in our simplified version, we ignored the existence of positrons, so we will skip this counterterm as well. The next step is to fit our three parameters to make sure that mass and charge renormalization conditions are satisfied. We will work within perturbation theory, so renormalization constants will be expressed as series in powers of the electron charge. And we are not going beyond the fourth perturbation order, so for us it will be sufficient to calculate this constant in their lowest orders. In other words, our new renormalized Hamiltonian is the same as the old one plus R2 plus W3. Next, we substitute the new interaction in the usual Dyson's formula in order to obtain S matrix. Then we collect together terms of the same order and obtain the following series. Here the first order term remains the same as before renormalization, so it is equal to 0. In the second order, we see the appearance of the renorm counterterm R2. Our mass renormalization condition requires the absence of renorm terms in the S matrix. So we conclude that R2 should be exactly opposite to the renorm part of the product V1, V1. Renormalization terms R2 and W3 participate in the third order renormalized S matrix. But one can show that all additional terms here are virtual, so their contributions vanish. Finally, in the fourth order, there are quite a few terms added by renormalization. The last product R2 will be cancelled by the fourth order renorm counterterm R4. Other new terms are supposed to cancel out all divergences that come from the original product of four V1 interactions. Let us now see how this cancellation is reflected in Feynman diagrams. On the left, I reminded the two interaction graphs in our original version of QED before renormalization. On the right, there are three new counterterms. This means that when constructing Feynman diagrams, we have to use these new vertices as well. By its operator structure, the new counterterm W3 is the same as our original interaction V1. So W3 is represented by the same two vertices. Only vertex factors are different. The counterterm R2 has operator A dagger A. So it is represented by a graph with one incoming electron line and one outgoing electron line. As we mentioned above, in the second order we must have exact cancellation of the R2 counterterm and the electron self-scattering diagram. But here is a problem. We know that the self-scattering diagram is infinite. So R2 is infinite as well. How are we going to use this infinite quantity in further calculations? The solution is given by the trick called regularization. It is introduced specifically to avoid manipulations with infinite quantities. We notice that infinities result from loop integrations at large values of momenta. So we can make all these integrals finite by introducing a cutoff radius lambda in the momentum space and agreeing to perform all our integrations only within this radius. Here is an example. Uh, the loop integral in the electron self-scattering term. At large values of the integration momentum, the integrand behaves as inverse square of momentum. So the integral diverges as a linear function of lambda. This is so-called ultraviolet divergence because it is associated with high values of momenta and energies. After we cut all our momentum integrals by the radius lambda, all relevant quantities become functions of this cutoff parameter. Of course, renormalization constants and counterterms tend to infinity at large values of lambda. But while lambda is finite, all quantities remain finite as well, and we can do sensible mathematical operations with them. At the end of calculations, we should replace the artificial cutoff by infinity, and if our theory makes sense, then all quantities with good physical meaning, such as scattering amplitudes, energies, and etc., must tend to some finite values in this limit. And hopefully these limits will agree with experiment. Renormalization theory insists that counterterms do not have physical meaning. So there is no problem if they diverge when the momentum cutoff is lifted. Later I am going to argue with this statement, but let us accept it for the moment. Here are some examples of the cancellation of divergences in the force perturbation order. On the left, you see one divergent diagram of electron-electron scattering. On the right, there is a diagram with a counterterm R2. It appears that these two graphs cancel each other exactly. Here is another situation in which the divergent loop is present in the internal line of electron-photon scattering diagram. Then the cancellation is not exact. There is a small residual term called radiative correction. These corrections are essential for achieving the good agreement with experiment, which QED is famous for. The counterterm W3 plays a similar role in cancelling divergences in vertex loops. It is remarkable that for each original divergent diagram, there exists a compensating diagram with a counterterm vertex. As a result, all ultraviolet divergences cancel out. So far, we discussed renormalization in the lowest force perturbation order. However, the same steps can be repeated in higher orders as well. There will be more diagrams, and the diagrams will be of higher complexity. But the good thing is that we can still use the same mass and charge renormalization conditions. And counterterm operators will remain the same. The only significant difference is that renormalization constants as functions of the cutoff parameter has to be recalculated in each order. This remarkable simplicity of the renormalization procedure is a characteristic of so-called renormalizable theories. QED is one example of such a theory. There are also non-renormalizable quantum field theories where the number of counterturn type increases in each new perturbation order, but we will not discuss them. So far we discussed ultraviolet divergences. They occur in loop integrals because the large momentum decay of the integrand is not fast enough for convergence. As we just established, this problem can be solved by renormalization. However, QEDS matrix terms also suffer from so-called infrared divergences. The reason is that loop integrals may diverge due to the presence of singularities at low integration momentum. These divergences have a true physical explanation associated with the zero photon mass. Since the photon is massless, each collision of charged particles may produce a huge or even infinite number of so-called soft photons, which have negligible momentum and energy. So, strictly speaking, each QED process, such as a collision of two electrons shown here, should be represented by an infinite number of Feynman diagrams describing creation of soft photons. These particles do exist physically, but usually they escape our observation. Special methods were developed to perform all these infinite summations and to solve the problem of infrared divergences, but we will not discuss these methods any further. Let me now say a few words about how renormalization is interpreted in most textbooks. It is alleged that renormalization can be regarded simply as a scaling of mass and charge parameters of the theory, while the operator structure of the theory does not change. In this logic, it appears that correct physical predictions are obtained with infinite values of the parameters m and e. And the argument goes that there is nothing to worry about. The values m and e used in equations of QED belong to non-interacting or bare particles which are impossible to observe. So the infinite values of these parameters are justified. And when QED interaction is turned on, the particles begin to self-interact. They surround themselves with clouds of virtual photons and electron-positron pairs, so that properties of these physical particles observed in experiments differ from bare masses and charges by an infinite amount. These explanations may sound plausible, and the common consensus is that all divergent problems in QFT have been happily resolved. However, Richard Feynman, who was the primary architect of the renormalization program, often sounded skeptical about its achievements. Here is one quote. "Today, we have no paradoxes, maybe. We have this infinity that comes in when we put all the laws together. But the people sweeping the dirt under the rug are so clever that one sometimes thinks this is not a serious paradox." Let me now summarize both achievements and failures of the renormalized quantum electrodynamics as I see them. Of course, the good news is that this theory provides an exceptionally accurate S matrix for charged particles and photons. All relevant scattering cross-sections agree with experiment in a broad range of energies. The electron's magnetic moment is often claimed as the most successful prediction of a quantity ever achieved in physics. Tiny corrections to the energy levels of atoms, called lamp shifts, agree with measurements very well. And taking into account that all these predictions were calculated from constellations of infinities, this agreement is nothing short of a miracle. But there is also a big bad news. Our theory lacks a well-defined Hamiltonian. The Hamiltonian of QED contains infinite counterterms, which do not allow its usage anywhere outside S-matrix calculations. In other words, the only quantities reliably predicted by QED are those directly related to the S-matrix. Notable examples are scattering cross-sections and bound state energies. However, the absence of a well-defined Hamiltonian does not allow us to use diagonalization to obtain wave functions of bound states. Also, we cannot construct the time evolution operator to study time dependence of states and observables at finite intervals. In my opinion, these are very serious drawbacks. They mean that the renormalized QED is not a complete and self-consistent theory. In the next lecture, we will see that there is a method which is called dressing that will permit us to obtain a well-defined finite Hamiltonian of QED and remove all divergences from the theory. See you next time. Thank you.